My dear students, I welcome all of you for today's session on design and analysis of algorithms. In this session, let me have a discussion about one more design strategy. And the design strategy is decrease and conquer. Okay, until last class, we had a discussion about divide and conquer strategy. Yeah. So first, before I state the agenda of today's session, let me tell you difference between decrease and conquer and divide and conquer. So in divide and conquer, you remember, right? How actually we used to solve? If problem instance is large, what I used to do? I used to divide problem into sub-problems with a newer instance. Again, if subproblem with newer instance is large, we'll keep divide the subproblem into further subproblems until all subproblems will have a smaller instance. Once the subproblems is with smaller instance, we will solve all the subproblems and we'll combine their solutions to get solution for the main problem. Got it? So, but here decrease and conquer. Okay, in decrease and conquer, what we'll do? We are given a problem with some instance. Got it? So, for the solution to that problem, I will represent. Okay, I mean, listen. You are given a problem with some instance. Okay. So what you will do? You will represent that problem. Okay, with the same with smaller instance means I'll divide the problem into sub problem. Okay, but what the new problem I'm going to get will be with some other smaller instance. I mean, you're given a problem with some instance. Got it? Then what you're going to do? You will divide that problem into a new sub problem. New sub problem will have a smaller instance. Got it? So the case is that you're going to solve the newer subproblem, and the solution what you will get for the newest subproblem will be nothing but a solution for the given problem. I mean, listen here, there is a relation between, okay, there is some relation between a problem with a larger instance and a problem with a smaller instance. I repeat, listen here. There is a relation between a problem with a larger instance to a problem with a smaller instance. If you're still confused, let me repeat. I'll give you better example for let me tell you. I'll give just I'll give you an example of binary search. Got it? So in binary search, what we used to do in binary search, we assume we are given an array of 20 numbers. Assume we are given an array of 20 numbers. Now I need to search for one particular element in an array. Assume that this is a successful case. So first, a given array is with how many elements? It's with the size is with 20. Now what I'll do? First, I'll compute the mid index. If a mismatch occurs between the mid element and the key element, next what I'll do? I will consider one of the input array. Got it? Means initially there were 20 elements. Now it has been divided into two subproblem. One subproblem, okay, depending on the key, whether the key less than the mid or key greater than the mid, I'll consider one subproblem. The other subproblem I'm going to discard. Clear? Again, in one of the subproblem, what I considered, got it? So I'll compute a mid. Clear? In that, again, mid, I will compare the mid of the subproblem, subarray with a key element. Now, let me assume again mismatch occurred. So what I'll do? the mismatch occurred, right? So again, this subarray, which was consisting 10 elements, clear? Because initially 20 elements were there, now it got reduced by off. Now there are 10 elements. Now what happens? This gets into two off with 5 elements in each of the two subarrays. So depending on the key, whether it's greater than the mid element of the subarray or less than a mid element of the subarray, I am going to discard one subarray of 5 elements. I am going to consider only one subarray of 5 elements. Got it? So means assume that in this subarray now what I have considered, okay, mid matches with the key. So mid matches with the key. Got it? Clear? Mid match with the key, right? So what you're going to do, what you're going to say? Successful search means actually I've given a problem with the instance of size 20, right? Got it? That was what actually I should have solved. I was given a problem of instance 20 elements. Got it? But uh, division process continued. Clear? Finally, I come up with a sub problem. Okay, I come up with a sub problem with instance of size 5 elements. Clear? I repeat, initially we are given an array with 20 elements. So we kept dividing because of a mismatch between the key and the mid element. At the last, I come up with the one sub problem in which the array was consisting 5 elements. In that, key got mashed. Got it? Means here in this subproblem, this solution of the subproblem, what it after solving the subproblem, what it returns? It returns successful search. Clear? So getting my point. So I solved the subproblem, right? So subproblem, what is stated? Successful search means actually that key element also exists in a given input array of size 20, right? So yeah, I mean to say, I said there's a relation between a problem with a larger instance and a relation between and a problem with a smaller instance. Got it? And I need to exploit this relationship. That is the strategy of decrease and conquer. Got it? Means actually I given a problem with larger instance to be solved, but I solved the same problem with some smaller instance. Got it? I solved the problem with some smaller instance. Clear? So I mean to say, I repeat, actually I given an array of 20 elements. Clear? In which I should have searched for the key element. Actually, at the last, what I solved a sub problem in which an array was consisting only 5 elements. And what the solution that has been written by this sub problem with the 5 elements? It's nothing but a solution for the given problem, right? With the 20 elements in an array. Got it? So this is the relation between the problem with the larger instance and the problem with the smaller instance. This relationship should be exploited and decrease and conquer strategy. I think you got to know the difference between divide and conquer strategy. And one more thing, while I've discussed binary search, right? When at the moment I winded binary search, I gave some remark about binary search, right? So I stated here, rather than considering binary search to be a divide and conquer strategy, I told you to consider as a decrease and conquer strategy. If you've forgotten, just go through that session video, and at the conclusion, you see I have stated a remark on binary search. Clear? So now coming to agenda. Got it? First, let me give you an introduction to decrease and conquer. Clear? So already now you came to know about decrease and conquer, right? So I repeat, what is an idea behind decrease and conquer strategy? We need to exploit, we need to identify the relation between a problem with larger instance and a problem with a smaller instance. Got it? So in decrease and conquer technique, okay, means Size, what I said, what we observed in binary search, initially size was 20, and next it got divided into two ops. We have considered problem with the size 10. Again, mismatch occurs between key and mid element, means two ops occur in one of five elements will be there, right? This process keeps repeating. Means what we observe stage by stage, the size of the instance got reduced. In binary search, it got reduced by op. Got it? So it need not get reduced by op. In some cases, the size of the instance may get reduced by some constant. Got it? Means in each stage, the size may get reduced by 1 or by 2, whatever it be. Got it? So there are three variations. One is decreased by constant. You got it? So next one is decreased by a constant factor. Factor means what? Some ratio, like binary search. It gets reduced by half, right? In each case, 10. Sorry, initial 20, 20 by 2, 10. Next, 10 by 2, 5. Next, again mismatches, 5 by 2, 2. So yeah. So variable size decrease means, okay, I'll give you a good example to demonstrate variable size decrease. Means the size of the instance, okay, I mean the problem's instance, there is nothing but size of the problem, stage to stage gets decreased variably. Means it won't, means there's a variable size decrease. Initially maybe 100, later it may become 75, later it may become 25, later it may become 2. Means stage to stage the size of the instance gets reduced. Okay, there's a variation. Got it? So these are the three variations of decrease and conquer technique. One is decrease by constant. In each stage the size get reduced by same value. Got it? By constant factor means like binary search. Okay. Next, variable size decrease means from stage to stage, how the size varies means size reduces means there's a variation. Okay, clear? So now coming to introduction. So what I said is based on exploiting relation between a solution to a given instance of a problem and a solution to its smaller instance. Means, okay, for some problem, okay, when I determine a solution for some larger instance, the same answer will be the solution for a smaller instance too. Got it? So there are such problems like what I said, binary search. Okay, and I need to exploit that relationship. I repeat, so there's a relationship between solution to a given instance. Okay, there's a relationship between a solution to a given instance of a problem and a solution to its smaller instance, and that relationship should be exploited. Okay, yeah. So once we come to know about that relation, we can solve either top down or bottom up approach. Clear? And I said there are three major variations, right? Decrease by constant factor, variable size decrease. Okay, so now coming to decrease by constant. See, decrease by constant means, just have a look at a slide. Okay, see here, I have given a problem with size n. Got it? I have given a problem with size n. Got it? So what I'll do, this may be now what happens, this problem need to be reduced to some other problem, reduced to some newer problem. It's not like dividing. Okay, it's not dividing a problem into sub problems, reducing the problem to smaller instance. Got it? Not dividing problem into sub problems, means there won't be many sub problems. Got it? There will be means the problem with a given size, say n, will be reduced to a newer sub problem with size less than n. Got it? So Initially, I given a problem with size n. Now, let me set constant, right? In this case, what happens? The size of the problem gets reduced. I mean, from a given problem, I will obtain a new problem. Got it? A new subproblem. The size will be a reduced one compared to a given size. So in this case, I'm saying size gets reduced by constant. So let that be constant be 1. Got it? So again, a problem is size n. Now this problem got reduced to a newer subproblem is size n minus 1. Got it? Suppose if required, okay, this subproblem could also get reduced to a newer subproblem. Okay, but now in second reduction, the size will be n minus 2. Clear? Because in each stage, the size get reduced by constant, that is 1. Clear? Now, assume that I solved a subproblem with size n minus 1. Okay? Assume that I solved the subproblem with size n minus 1. I got a solution, right? So, and this solution, what I got is nothing but the solution for the original problem too. Got it? Clear? What the solution I got for this subproblem? Okay, it's nothing but a solution for the given original problem. Okay, that's what I said. What the strategy says? I need to exploit the relationship. I need to exploit the relationship between a solution to the given original problem and a solution to the subproblem. Clear? So I think you got to know about strategy of decrease and conquer, right? Once in divide and conquer, we have many subproblems. Clear? But in decrease and conquer, the given problem will get reduced to a newer subproblem and only one subproblem. Got it? So now, and one more thing very important, strategy, what it says, exploit relationship between solution to subproblem and solution to original problem. Got it? So let me give an example for decrease by constant. Okay, so decrease by constant. In decrease by constant, a better example I've taken is computing a power n. Okay, awesome. You can write an algorithm for this. Okay, you can either develop a recursive algorithm or you can even develop a non-recursive algorithm. But I have not designed an algorithm in this case, but it's very easier. You can design yourself. Okay, if you know to set up a recurrence relation with the appropriate initial condition. Clear? If you know to set up a recurrence relation with the appropriate initial condition, you can design a recursive algorithm for this. So I need to compute a power n. Okay, the condition is that a can be greater than or equal to 0 because we have 0 power anything is 0, right? So a can take a value 0 2. This says that a is greater than or equal to 0 and n is a non-negative integer because n can take value 0 1 2 3 so and so but not negative. Clear? So the constraint here is a can be 0 or greater than 0. N is a non-negative integer. Okay, so we know what I can do. There's assume that there's a problem. Okay, this problem. Okay, I need this assume there's an algorithm. There's an algorithm. Okay, that computes a power n. For that algorithm, what I'm going to give as an input a and n, and assume that when you give this particular input a and n, assume that algorithm is going to return you the value of a power n. Got it? Now, suppose for this algorithm, rather than giving inputs a and n, assume I have given a and n minus 1. So what that algorithm will compute now? A to the power n minus 1. So if I have a to the power n minus 1 and if I multiply a to that, what I'm going to get? A power n. Got it? So this is what the relationship. Got it? I said, right? I need to exploit relationship between a problem with a given instance to a problem with a smaller instance. Got it? Let me tell you. Okay, I need to compute a power n, right? So what I'll do, I will compute a power n minus 2. For that, if I multiply a square, I'll get a power n, right? Clear? So this is an example of decrease by constant. Means I repeat, I should compute a power n. Okay, but I will compute a power n minus 1. Once I compute a power n minus 1, let me multiply a to that. Got it? So what I'll get? A power n. So the question next is, I should compute a power n minus 1. To compute a power n minus 1, what I can compute? Let me compute a power n minus 2. For that, let me multiply a. Clear? So similarly, to compute a power n minus 2, let me compute a power n minus 3. For that, let me multiply a. Got it? So this is an example for decrease by constant. Now, decrease by constant factor. Got it? The better example is binary search. Got it? So binary search, just now explained you about binary search, right? When I started this session to give a difference between decrease and conquer strategy and divide and conquer strategy. Got it? So again, I repeat, okay, look at the slide and remember, in divide and conquer, problem gets divided into several sub-problems. But in decrease and conquer, what I said, problem gets reduced to a newer sub-problem. Gets reduced to newer sub-problem and only one sub-problem. Okay, got it? So let me say this is by constant factor. Constant factor means a factor keep reducing from stage to step by half, or keep reducing stage to step by 3 by 4. Got it? Or keep reducing stage by 1 by 4. That's we call factor. So in binary search, okay, initially let me say 100 elements were there. If key mismatches with mid, what I'll do? I will divide that into 2 offs and I'll discard 1 off and I'll consider the other off with 50, right? Next, again in this off, okay, if a key mismatches, what I'll do? Again, I'll divide into 2 sub-offs of 25 each. Clear? Then other of one of I'll consider, the other of I will discard. In the considered of, again I'll compare key with a match. If match occurs, successful search. And the successful search is nothing but solution for a given array of 100 elements, right? Got it? So this is decrease by constant factor. Decrease by constant factor means in each and every stage, size get reduced by factor. So factor may be an off, like binary search. So here one example what I've given. This is just I will look simple example. Okay. Again, I need to compute a power n. Okay. So to compute a power n, let me assume you have assume first there are 2 cases. Okay. Let me assume n to be even. Got it? So n to be even means assume you need to compute a to the power 6. A to the power 6 you need to compute. But you compute a cube. You compute a cube. That is a to the power 6 by 2. It's nothing but a cube. If you have a cube, square a cube, what you're going to get? You're going to get a to the power 6. Clear? I need to compute a to the power 6. What I'll do? I will compute a cube and I'll square that. That's nothing but means the relationship. Now I should determine that's what the decrease and conquer strategy says, that the relation between a power 6 and a cube is that square of a cube is nothing but a power 6. I repeat, the relation between problem with a given larger instance and problem with smaller instance should be exploited. And in this case, a to the power 6 is nothing but square of a cube. Clear? This is the relation between a power 6 and a power 3. Got it? Means square of a power 3 is a power 6. Now, if n is 0, it's understood a power anything power 0 is 1. Got it? So now, if n is odd, okay, let me say a power n is 7. In that case, what I need to do, if n is odd, okay, I need to compute a to the power n minus 1 by 2. Means a to the power 7 minus 1, that is 6 by 2. That's nothing but a cube. Square the a cube, what you are going to get? A to the power 6. For that a to the power 6, you multiply a, you're going to get a to the power 7. Clear? So when n is odd, say a to the power 7 to be computed. Okay, I will compute a to the power 7 minus 1, that is 6 by 2, 3. I will compute a cube. I'll square a cube. I'll get a to the power 6. I'll multiply a. Got it? So this is about decrease by constant factor. So the last variations, variable size decrease. Okay, I'll explain you through a very interesting algorithm named Euclidean algorithm. Hope you might add this algorithm in your CCT. Okay, if not, let me explain you this. This is very important algorithm to compute GC. Okay, greatest common divisor. Okay, so variable size decrease, I said what I said. See, in the first case, okay, by a constant, okay, there, suppose I want to compute a power n, means I will compute a power n minus 1. For that, I will multiply a. Is it here? To compute a power n minus 1, what I will do? I'll compute a power n minus 2. For a power n minus 2, I'll multiply a. In next stage, to compute a power n minus 2, what I'll do? I'll compute a power n minus 3. For that, I'll multiply a. Means in each stage, the size, that is n, was getting reduced by 1. So that is decreased by constant. Got it? Decrease by constant. So decrease by factor, if I say I wanted to compute a to the power 16, but I'll compute a to the power 16 by 2. That's nothing but what? 8. See, I need to compute a to the power 16. I will compute 8 to the power 16 by 2. That is 8. And I'll square, I'll get 8 to the power 16. Got it? I repeat, to compute a power 16, I'll compute a power 8. Got it? If I square a power 8, I'll get a to the power 16. To compute a power 8, okay, I will compute a power 4. Then, if I square a to the power 4, I'll get a power 8. Then to compute a to the power 4, I'll compute a square. Got it? Then I'll square a square, I will get a to the power 4. Means stage to stage, the size was getting reduced by a factor, that is exactly up. It was 16, got reduced to 8. Then it got reduced to 4. Then it got reduced to 2, and so and so. Yeah. Now variable size decrease means, okay, the size varies randomly. Got it? Not by a constant or not by a factor. Random size variation. Okay. Let me take you one example. Okay, GCD. All of you listen this algorithm very carefully because it is very important exam point of view. Got it? Euclidean's algorithm for computing the greatest common divisor of any two non-negative, not both 0. Got it? Means you are given two integers, you need to determine its GCD. Condition is that those two inputs should be non-negative, okay, and not both 0. Means one of the two inputs can be 0, but not both can be 0. Got it? So what is condition for inputs in case of GCD? Suppose inputs are m and n. Those m and n should be non-negative. Okay, and either of m and n, either one of m and n can be 0, but not both m and n can be 0. If this we call a legal input. Okay, this we call a legal input. So now to compute GCD, okay, we'll see the methodology, the logic behind computing GCD. Okay, logic behind computing GCD. So before that, just I'll tell you, I'll show you a relationship. Okay, what decrease and conquer strategy says? What decrease and conquer strategy says? Exploit the relation between a problem with a given larger instance and the problem with a smaller instance. Clear? You need to exploit relation between a problem with a larger instance and a problem with a smaller instance. Got it? So now, what is that relation? There's that relation has been in GCD. Okay, recurrence relation. We have recurrence relation. Okay. Just look at GCD of just on the slide. Just have a look at recurrence relation. Okay, what I have written: GCD of m comma n equals GCD of n comma m mod n. Mod means modulus operator, means it gives remainder while m is divided by n. Clear in this case? Got it? So this is the, it says relation. Okay, see, for example, in example, I have just looked at an example. GCD is some algorithm. When I give two inputs to that algorithm, that gives me an answer, GCD of those two input numbers. Okay, so now what is an input to this GCD in an example? It's 60 and 24. Just observe the input to GCD is 60 and 24. Now, decrease and conquer strategy, what it says? Exploit relation between the problem GCD with these two instances, that is 60 and 24, and a problem with some other smaller instance. Got it? Less than 60 and 24. Clear? So now, according to recurrence relation, okay, what happens? Recurrence relation, what it says? GCD of m comma n equals GCD of n. So what happens? The second argument and first invocation will become the first argument in next invocation. I repeat, second argument, that is n of current invocation. Current, that is first invocation, assume it to be first invocation, becomes first argument for the next invocation, that is second invocation. So GCD of 60 comma 24 equals GCD of 24 comma. What is next? We'll see. What is the 12? How we got 12? We'll see. See, got it. So 24 in first invocation, it was a second argument. Clear? Now it got first argument. So initially first argument was 60. Now it got reduced to 24. Clear? Got it. So between what is the difference between 60 and 24? See, between 60 and 24, the difference is 36. Got it? So now for the second argument 12, right? It's nothing. What is the 12 means? I divide m by n. The remainder is 12. 60 by 24. Remainder is 12. Got it? So next, this recurrence will continue. Okay. What happens? Simplification continues. Okay. This becomes again what I said. Second argument of current invocation. Okay, let me say current invocation, that is the second invocation, that is second argument is 12. It becomes third, it becomes first argument for third invocation. Clear? So in third invocation, 12 become first argument. So next, in second invocation, m is 24, n is 12. So remainder after dividing 24 by 12 is 0. Got it? So now one of the two arguments is 0. when one of the two arguments is 0, okay, we look at initial condition. What it says, GCD is M. Okay, so now among these two arguments, 12 and 0, 12 is a non-negative, non-zero. So GCD is 12. You can use your skills that has been taught in your school lab to compute GCD and check GCD of 60 and 24, 24 and 12, 12 and 0 is always 12. See, stage by stage, from 60 and 24 got reduced to 24 and 12. Then 24 and 12 got reduced to 12 and 0. So there's a variable size decrease. Got it? So this is an algorithm. According to initial condition, sorry, when m greater than 0, that is wrong. That is actually initial condition are written when m greater than, sorry, that should have been written as n equal to 0. Okay, one small mistake is there. For initial condition, GCD of m comma 0 equals to, okay, then that's not a mistake. Okay, right, nothing error, nothing error. Initial conditions correct. Okay, GCD of m comma 0 equals m means second argument n is 0, right? So if n is 0, what is GCD? M. So return m. If n equals 0, return m as GCD. Yes, return. Invoke further with what? N and m mod n. Yes, return Euclid. I have given an algorithm instead of GCD, I have given name as Euclid. N comma m mod n. Now I have designed a non-recursive algorithm too. Okay, a non-recursive algorithm. Okay, it's very simple. When see, according to initial condition, okay, just look at example. There were 3 stages. And I have not proceeded for the 4th stage because n got 0. When n becomes 0, that is the end. No need of further iterations for the stages. Return what is the value in m as GCD. Okay. So now this is, it says, so first what I this is a non-recursive algorithm. So initially let me check whether given input n is 0. If not 0, if it is not 0, right? In this, look at iteration 1, n is 24. Whether it's equal to 0, it's not equal to 0. So what I will do, I will let me compute remainder by dividing 60 by 24. Remainder I've got 12. Got it? So next what I should do, just what we have seen, the second argument, that is n becomes first argument. So what is present in iteration 1, n is 24. It will move to, it will be copied to m in second iteration. Got it? Remainder 12 will be copied to n. Got it? So while n not equal to 0, first compute remainder r equals m mod n. Then copy n to m, r to n, n to m, r to n. Now check in the second iteration, n is not 0. Then third iteration comes. In third iteration, n is found to be 0. Stop for the iteration. So what is in m? That is GCD. Again, 12 is GCD. So got it? So clear, this is variable size decrease. So m got reduced by 60 to 24 to 12. And from 24 to 12, 0. Okay, this is about today's session. Thank you for listening.